decode, execute, man memory and write back. The second instruction, fetch, because the second instruction is independent, so it can proceed. Decode, execute, man memory and then what? Write back. And please remember, R5 will be available here. R5 is available here. In which clock cycle? Memory cycle. So R5 is available here. But we need this. We need R5. We need R5 in the decode stage of I3. And if you look at I3, so now we have which? We have the green color, so fetch and then decode. So we directly code it from here. We don't need a star here. And then execute, man memory and write back. How many clock cycle? 1, 2, 3, 4, 5, 6, 7. No stall. No stall at all. Now, if we have no forwarding, then we have fetch, decode, execute, man memory and write back. Since there is no forwarding, so R5 is now available where? Here. Because we have no forwarding. And if there is no forwarding, the result will be overwritten in the last clock cycle, independent of whether. And please remember, in the first half or the second half? Writing in the first half. Yeah? So then we have, but the second instruction is independent, we can proceed it. So fetch, decode, execute, man memory and write back. But now the third instruction is dependent. And we need here in decode stage. So now we have the third instruction, which is actually the fetch stage. We need it here. Can we go backward? No. Okay, now this is forwarded from where? Forwarded from where? LUOut1, LUOut2 or LMD? LMD. Why LMD?
Because
LDR. LMD. Then we need a stall here. Then decode, execute, man memory and write back. And we need an extra stall because there is no forwarding. Any question? Should we proceed? Okay. Should I wrap this up? Okay. So nowadays, we covered all of this stuff. So now what I am going to do? So I am going to the lecture slide, and all these things will be done here. So can we see here? Again the same pipelining with the forwarding. We have a load instruction and then we have add. So it means the load instruction, the add instruction is dependent on the load instruction, which is successive. Can we go backward? No. How many stalls? One stall. And we discuss this scenario. So there will be one stall. Okay, so now we have the data hazard. So now we have a load hazard. Load. Okay, so can you see here? Now, data access is here, instruction hazard is to resolve conflict. Okay, so can you see here? Now, again, the same example. This is a structure hazard. One instruction is in the memory stage, and other instruction is in which stage? Decode stage. So we need a separate instruction memory and separate data memory. Remember? So we need a stall here. What is the? So please remember, this instruction is a load instruction, and even I plus 3 is not dependent on the load instruction. But we need to access the data from memory, and this instruction I plus 3 is reading the instruction. Can we do it at the same time? No. So what do we need to? We need to stall I plus 3. What is the solution to it? Separate instruction and data memory. So if we have separate instruction data and data memory, so basically what we do, so we do it, so this is resource duplication. Also the structure hazard in the register file. We have no, so okay, one register is write. We are writing one register in the write back stage. One instruction is writing and other instruction is reading. And if it's the same register, can we do read and write at the same time? No. So what do we need to do? Write in what? The first half and read in the second half. So now this is the explanation. So now let's go through all the things. So how do we enable read and write at the same time? How it works? We register file in two stages, either with the half cycle. So write in the first half and read in the. And how much can you see here? So it means that if 1, 2, 3. So if this is instruction I, so this instruction will be what? I plus 1, I plus 2 and I plus 3. So we write register for instruction I in the first half and read in the second half. For instruction, which instruction? I plus 3. Can you see the difference in the pipelining stages? Now we have the data hazard. Now please remember, now can you see here? Let's assume we have no forwarding. We are writing register R1 in which clock cycle? For the add instruction. Clock cycle 1, 2, 3, 4 and 5. And no forward. Can we go backward? No, because this instruction is requiring R1 in the next clock cycle. So we cannot go backward. What is if there is no forwarding, how many stalls will be there? 2 stalls. Because we cannot go back. R1 is updated in the first half. Can we go backward? Updated R1 is required in clock cycle 3 because it's in decode. So basically in clock cycle 3 we need, and this is actually, if you look at here, so this is in clock cycle 3. This is actually op 1. This is op 1. We are reading this R1 in the second half. Clear? What kind of hazard is this? Data hazard. Can you go backward? No. And data hazards. Why there is a data hazard? Because the source of this second instruction is dependent on the destination of this instruction. And even there is a dependency between I2 and I1 and I3 and I1. There is a dependency. How to resolve this dependency? This is the data hazard. Okay, even if this is dependent, but there it will not create a hazard. Why? Because this is I plus 3. So in this case, the value of R1 will be overridden in clock cycle 5. So there will be no hazard between this instruction and this instruction if these two instructions are independent. Now these are the data hazards. No data hazard occur in instruction I plus 3 in the following instruction. What's the solution? Forwarding. Can you see here? Data hazard. So we forward it from here to here. We call this is execute / memory, but what was the name data I gave it to it? LEOut 1. Clear? So we have removed the first. We have removed the first red line because we cannot go backward. But now the temporary computation is in LEOut 1. So we are providing it from LEOut 1. Can we go backward in the absence of forwarding? No. Can we go backward? No. Then now, what we need? So LEOut 1, the result is now in LEOut 1. And here, it is LEOut. Clear or not clear? Okay. Is there any load instruction here? No. So if there is no load or store instruction, there will be no data hazard. But what if the following instruction is dependent on the preceding instruction and the preceding instruction is a load instruction? Even with forwarding, there is a problem. Clear? So now we go to the next slide. Clear or not clear? Any question? Now, stall. Still, sometimes stalls is necessary. Which instruction is this? Load. And the following instruction is dependent on what? The load instruction. And when it will be overridden? The clock cycle 4. And where is now the result? LMD. Can we go backward? No. We can, because we need this result here. But what we need? So we need how many stall cycles? One stall cycle. Any question? Any question? Should we proceed? Okay. Now until unless we have studied two types of stalls. Okay, stall may occur. Can anyone elaborate? Now, until and now we have studied some stalls. Stalls occur because of what? Can anyone tell me? Can stall occur because of what? Structure hazards. Now let's assume if we have combined memory, one instruction is loading data, and other instruction we are reading the instruction. We have a combined main memory. Even these instructions are not dependent, but it will create a stall. Why? Because we cannot do the two memory operation at the same time. What do we need to do? Introduce data the resource duplication. And what is resource duplication? Instead of having one memory, we have two separate memories. One memory is dedicated for instruction and another memory is dedicated for what? Data. Clear? This is called as resource duplication. Then we also have a structural hazard in the register file. What was the problem? We were writing one register in the write back stage, and if you are reading the same register in the decode of the following instruction, can you do that at the same time? No. This was also an example of which hazard? Structural hazard. How did we avoid this problem? No. So we have a register file. Here we are writing the same register. Let's say we are writing the same register R5 in one clock cycle, and we are reading the same R5 for the next instruction. So then there is a problem. We cannot read and write at the same time. What do we need to do? We need to write first for the first instruction and read second. So we write in which half cycle? The first half cycle and read in the. So we have the updated value. Got it or not got it? So we also avoided the structural hazards. Any question? Any question? Then the hazard comes because of the dependencies. Because if there is no forwarding, and if the result of the following instruction is dependent on the preceding instruction, so the result needs to be written into register file in clock cycle 5, which is the first, and we need that value in clock cycle 3. So we have a hazard. We cannot go backward. So what is the solution? We do forwarding. We can forward. From where we can forward the result, intermediate result. We can forward the intermediate result from where? ALOut 1 or ALOut 2 or LMD. So we can. These are the different forwarding feedback paths. Clear or not clear? Now another complexity arrives if there is a control hazard. And what is the control hazard? Hazard because it's the branch hazard. Okay, now let's assume if we are fetching. So let's assume I will explain this in an example. So let's assume we have this first instruction, which is I1, which is the fetch instruction. So I1, where I2, this way I3. First we need to fetch I1, then we need to fetch I2, then we need to fetch I3. And let's assume all of these are sequential instruction. These are sequential instruction. But let's assume now we have I4, which is a control instruction. Control instruction will change the flow of the program. So from control instruction, we will jump to some instruction. Let's assume that instruction is I100. Should we fetch I5? Should we fetch I5? I'm asking. Let's assume we fetch the first instruction, we execute. So this is add instruction, this is subtract instruction, and this is divide instruction. Then we have we have this instruction, jump I100. Should we fetch I5? No. Which instruction should we fetch? I100. Let's say we jump to I100. So now we fetch this I100, and then the execution will start with that. Then which instruction should we fetch next? I101 and I102 and blah blah blah. But now the problem is that when do we know that it is a jump instruction or control instruction? During the decode stage. So the problem is that since we are in the pipeline, so we have to fetch what? I5. I5 will be fetched unnecessarily. But what we need to do, when we jump to that instruction, we need to do what? We need to flush I5. Even if we have fetched I6, we need to flush I6 because we do not need I5 and I6. They are unnecessarily fetched. They are unnecessarily fetched. Okay? So this kind of hazard is called as which hazard? Control hazard. control hazard or branch hazard. And control hazard or branch hazard, we need to, okay, now the problem is this. Okay, there are two possibilities. If the branch is taken or the branch is not taken. I will explain this with an example. Let's assume if this I4 is this instruction BRZ label. We are jumping to label. Which flag we are checking? Which flag we are checking? Z flag. So okay, now if we say if Z flag is equal to 1, which instruction should we fetch? No, we say BRZ label, and label is actually the address of I100. So let's assume this is my label. If the condition is true, should we jump or should we not jump? We should jump. Which instruction should I fetch? Because the instruction which is stored at an address of label is I100. So which instruction should we fetch? I100. If the condition is false, fetch I5. So now in the branch instruction, so basically now we have, please remember, now we have, so do we have one target or two targets? Two targets. So can we say, okay, now, so now conceptually, we can say, so now what I'm going to do, so now we can say here, and please remember, in this case, I'm just giving an example, it is BRZ, it can be BRN, it can be BRP, it can be BRNZ, we got BRP, and this can be any different combinations. So can you see here, now, so there are two things. Okay, now, we can say if the condition, the branch condition is true. So generally you can say, if the branch condition is true, what should we do? Jump to target. Jump to target. And what is now the target here in this example? I100. And if the branch, so basically now I'm just generalizing. Why I'm generalizing? If the branch condition is true, we should jump to the target address. I'll explain this with an example. So now let's assume there is a condition here. So now here the sequential instruction, and then now the control instruction. Okay, please say jump to Dalia. Jump to Dalia. Okay, now jump to Dalia if she is wearing glasses. Condition is true or false? Because she is wearing glasses, I will jump to that. Now the condition is true. So now jump to Dalia, so this jump. Clear or not clear? Okay, now what is the target address? Let's assume her address is 10 and your address is 100. What will be the offset? Remember, target minus incremented PC. That is the offset. Remember? So that's the target. Okay, now please pull up your glasses. Now jump to Dalia. Is she wearing glasses? No. Where should I jump? To the next sequential instruction. Clear or not clear? So now we can say if the branch condition is true, we jump to the target address. And else, what does it mean? Branch condition is what? False. If it's false, where should we jump? Jump where? The success, the following instruction. And what is now the following instruction in this particular example? I5. Now we are jumping to now I5. Clear or not clear? So now this now a complicated situation. Now So the question is that, should we, now there are two solutions to this problem. There are two solutions to this problem. Should I rub this off now? Should I rub this off? So now there are two solutions to this problem. And what is that solution? There are two things. One is called as redo instruction fetch. Redo instruction fetch. And I'll explain this with an example. So should I rub this off? Okay. Okay, now please remember, if we jump to the following instruction I5, if we jump to the following instruction I5, where is that address stored? Very good. It is stored in NPC. Please remember, in the same concept. If we jump to the following instruction, the address is stored where? NPC. And if the branch condition is true, if the branch condition is true, where should be the target address? Where should be the target address? Can you tell me? What should be the target address? Please remember, the target address will be NPC plus what? Remember? And remember in LC3 we can always say incremented PC. And what is actually incremented PC? NPC. Remember or not remember? Because you know what, I'm going to repeat all of the previous stuff now. This is just like even I'm doing a lot of repetition. I'm doing a lot of repetition now. Okay, now what we are going to do? Okay, now listen. Now I'm not talking about I1, I2, I3. Forget about I2, I1, I3. Listen, we have I4 now. Now this is my I4 now. So now we fetch instruction I4, then we decode it, then we execute it, then in memory, and then we have write back. Clear or not clear? So these are the 5 cycles of I4. And I4, please remember, now I4 is which instruction? Which instruction is I4? It's a branch instruction or control. So it's a branch instruction or control instruction. So let's say it's a branch or control instruction. It's a branch instruction, so we need to first fetch it, then we need to decode it, and we execute it in memory and write back. So this is the flow of the control instruction. Now, the problem is that, okay, now we know in the decode stage, so we do not know that it's a control instruction, and we know in the decode stage, yes, in the decode stage, because we have fetched the instruction. When we have fetched the instruction, it will go to IR. Because the PC will go to MAR, PC will go to MAR. We will fetch the data in MBR, and from MBR, where did it go? To IR. Clear? So now the instruction, so this I4 in the decode stage is now the instruction. Please remember, the machine code of I4 is now where? In IR. Now we are decoding the instruction. So we are now decoding the instruction by looking into the opcode field of the instruction. And looking into the opcode field, we know, oh, the opcode is now a branch instruction. Since we have now the branch, we do it now. Now we have come to know, oh, it's a branch instruction. So now there are two possibilities. So the following instruction, I5. So okay, now this I5 should be fetched here. Am I right or not? So actually I5 will be here. I5, okay, please remember I'm now using different colors. I5 is which color now? Green color. And now we have other color. So I will say, okay, now listen, this is I100. And I100 is now black color. So we fetch, one option is to, we fetch which instruction here? But now we know that this is now a branch instruction. Now there are two possibilities. We redo fetch. And in that case, in decode stage, we know that now the branch is taken or not taken. The branch is taken or not taken. So in the first case, we call it redo in instruction fetch stage. So in the next clock cycle, so We ignore this thingy, we flush it. And then we refetch I5. So, okay, now there are two possibilities. We either fetch I100, if the condition is what? True. And then we fetch I5, if the condition is what? False. This method is called as redo fetch. And in this case, how many stalls will be there? One stall. How many stalls will be introduced? One stall. Efficient approach or inefficient approach? I'm asking. Efficient or inefficient? Inefficient. Why it is inefficient like that? Because we are refetching I5 in the next clock cycle twice. Can you see here? We have fetched I5 here, but we are refetching it. Clear? So if the branch is untaken, the stall is unnecessary. Why the stall is unnecessary? So it means that now we introduce a stall here. So we flush it so we can see. So we have this here. And we have a stall here. Now what we are going to do? Now there are two scenarios. There are two scenarios. Scenario number one. The branch is taken. If the branch is taken, so we fetch it here, then fetch it here, then we decode, then we execute, then memory and write back. And then for the following instruction, so now which instruction? So we have the I4 here. So this is my I4 now. Then please remember we have a stall here. Stall, 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 and stall. And then if the branch is taken, which instruction should we fetch now? I100. So now we are fetching I100. And I100 is fetched now here. Fetch, decode, execute, memory, and write back. How many stall cycles are introduced? How many stall cycles is introduced? One. One stall. This is one stall. Clear? This is one stall. Okay, now scenario number two. We have I4, which branch is not taken. Branch is not taken. So we fetch here, decode, execute, memory, and write back. And again, then we have a stall here, stall here, stall here, and stall here, and stall here. And which instruction will we fetch now? I5, fetch, decode, execute, memory, and write back. So we have an unnecessary stall for scenario number 2 or scenario number 1? Scenario number 2. Because if we are not redoing it, so what we can do, so when we fetch I4, so it is actually fetch, decode, execute, memory, and write back. And still we have the follow address of instruction 5, which is stored in NPC. So what we can do? We can do here I5. So we fetch it here. And then we decode it here, execute, memory, and write. Do we need a stall here? No. So redoing is a good example, a good approach or bad approach? Refetching, redoing instruction fetch. Good approach or bad approach? Yes, it is a bad approach if the branch is untaken. And it's a good, it's a normal, there will be no stall if the branch is taken. Clear or not clear? So now what we do, so we have another, so can you see? We are refetching it, the target. Either we are fetching I4, I5 here, or either we are fetching I100 here. Now the second case. So it will introduce the stall here. Got it or not got it? Now the second scenario. So, in the second scenario, should I rub this off? What's the second scenario? So So this method is called as redo IF. It will cause an unnecessary stall if the branch is what? The branch is not taken. Now the second approach. Flush the successor if the branch is taken. So we flush the successor if the branch is taken. So now let's we have I4 here now. Fetch it, decode it, execute it, memory, and write back. And then we have I5. Okay, we fetch I5, no problem. So we are fetching I5. So it's fetch here, decode here, execute here, memory, and write back here. But now, at the decode stage, at the decode stage, we know it is a branch and it is taken. So what we need to do, so for the I5, what we need to do? Help me. Do we have these stages? Decode, execute, memory, write back. What do we do? Flush, and flush. And what instruction should we fetch now? Because now the branch is taken. I100. And I100 is fetching which clock cycle? The next clock cycle. So we fetch here, decode here, execute here, memory, and write back. And when I100 is fetched, which instruction should we fetch next? I what? 101 and I102. Assuming that I101 and I102 are the sequential instruction, not the branch instructions. Even if they are branch instructions, then it will complicate the issue. So we assume that all of these instructions are what? These two. Sequential instruction. So this is our assumption. And then we can fetch decode. And please remember, even I100 and I102, it all depends on the dependencies of the preceding instruction. So how many stall cycle will be introduced? It depends on the dependencies. It also depends on the scenario, whether the scenario of the forwarding case, the scenario of the no forwarding case. So there are multiple scenarios. You got it or not? Any question? Okay, now, so now we flush it. But if the branch is untaken, so do we need a stall? No. So if the branch is untaken, so what we need to do, so now I'm going to do, so I'm going to interrupt this off. Second approach. If the branch is not taken, so we fetch what? I5, then we decode it, then we execute it, then we memory and write back. Do we need to flush I5 if the branch is not taken? No. Which instruction should we fetch next? I6. So I6 will be fetched next, assuming that I6 is a sequential instruction. This is a fetch, decode, execute, memory, and write back. So there will be no stall. There will be no stall. Any question? Okay, so now I will finish until here. So now until the branch taken and not, I'm not going to go into more detail from here. Now this will be the content pipeline. Pipeline is now finished. Clear? So now from the next, from tomorrow onward, we'll start with a new topic. Please remember, the new topic will be included in midterm 2 and in the final. So the new topic will be the memory system design and the cache topic. The new topic. So what?
This is tomorrow's quiz.
No, this is not for tomorrow quiz. For tomorrow quiz, the dependency is not covered. This is for your midterm 2. From midterm 2 onwards. So the dependencies is not covered. Okay, so what I'm going to do, so I'll give you a question now. So you can start with the quiz. So this is a mock quiz. So please do it.